All right. Thanks a lot. So I was asked to talk today about some of the results on Summit and Sierra and how that's influencing Exascale. And so we'll talk a little bit about Frontier at the very end. But first I wanted to start out by just giving us a little bit of an overview of the Summit and Sierra systems. So Summit sits at Oak Ridge. It's an IBM system. It's got a peak of 200 petaflops. And so that makes it the number one system in the world right now. But I really think of that as being a very fleeting sort of thing. Being number one, all that really means is you got a target on your back and other people are shooting for you, right? What's more interesting probably about Summit is that we're talking about getting to exascale. And in fact, if you're doing things like artificial intelligence or data analytics, Summit is already there. It already has the capability of over 3 exaflops in half precision. And so in that respect, it starts to make a fuzzier definition of what do we mean by an exascale machine. We'll talk a little bit more about that as we go through the presentation today, because we actually have full-scale applications, real applications that are actually running over an exaflop on this system. But let's talk a little bit more about the overall system. It's 4,600 nodes, so a fairly small number of nodes when our users first learned about it. So it's like, wow, that's going to be a lot easier to program than what we've been having to do in the past. It's got a fat tree network. It's a dual rail Mellanox, so it's fully non-blocking interconnect between it. We've heard today several different other sites that have put file systems in place, and they have 30 petabytes or 50 petabytes. This has a huge amount of storage actually hooked in the file system of Summit. It's got 250 petabytes of the IBM GPFS file system, and it has a very high bandwidth to it, 2.5 terabytes per second. Each one of those nodes has 2 IBM Power 9s on it, has 6 voltas, so it's a gigantic node, and that node itself has over ½ terabyte of memory on it, and all of that memory is coherent across the node. In addition to that node having ½ terabyte on it, it's got another 1.6 terabytes of non-volatile memory, so there's a huge amount of memory on that system. Let's quickly then jump to Sierra and do a little overview of it. And one of the interesting things that people don't really know, probably don't know about in this room, is that it's made from the same parts, but it actually has a different architecture underneath the covers. So I'll just sort of illustrate what those differences are. So if we look at the node of the Livermore system called Sierra, it actually has 2 Power 9s and only 4 Volta GPUs in it. And not only that, it's not just that they eliminated 2 of the GPUs, but they rewired the node because of that, to try to take advantage of additional bandwidth that would be available because of it. And because of the smaller number of GPUs, then the amount of memory on the nodes is different. Their interconnect for the overall system is different from Summit. So theirs is a single plane Mellanox tapered network. And then I still wanted to point out that even with these differences, Sierra is also a system out there today that has more than an exaop of capability built into it. So it's got over 2 exaops available in that particular system. I want to talk a little bit more and get into the nitty-gritty details. This slide, I have 2 points I want to make. One is, okay, yeah, there's this really complicated diagram just to tell you all of the details of the Summit node, the 6 GPUs, the 2 CPUs. We're not going to get into the details there. I just wanted to one, make it available to you, but also to show a little bit about how it differs from Sierra. So you can see that you could imagine, here's the Summit node. If we take off these 2 GPUs on either side here, eliminate them from the nodes, but then take all of the links, these 50 gigabyte links that are going to those GPUs, and run those to the CPUs and to the other GPUs that are available, what you get is a much higher bandwidth. So you get 75 gigabytes per second between the CPU and GPU instead of 50, and that's what Livermore was really shooting for. They wanted to get more bandwidth between the CPU and GPUs, and they also, because they didn't have the experience Oak Ridge has had with GPUs for such a long time, they didn't want to overwhelm their users with so many GPUs in the first big system that they got. So that's the first thing I wanted to make a point. And the second point about this particular slide was just to show this progression, because it'll lead naturally to our conclusion at the end. So a Titan node that we had before we got Summit was 1 GPU per CPU. Then we look at Sierra node, and it's got 2 GPUs per CPU. And we look at the Summit node, and it's got 3 GPUs per CPU. I don't know if anyone sees a pattern there. And in fact, when we get to Frontier, we'll see that it's going to be a natural progression of that particular architecture. And more importantly, in the next few slides, I want to try to explain why that's the case. First off, we talked about Amazon services and various other people that have put together NVIDIA-based machines or GPU-based machines. It's amazing to think of how many voltas are actually in this machine available for people to use. 27,000 volta GPUs inside this machine. And each one of them is optimized for AI performance. So each one of those voltas can perform 7.5 teraflops. That's what we thought about when we first selected this machine. It was going to be very powerful. The GPUs were very powerful. What we didn't know until it was actually delivered and NVIDIA actually then exposed to us is, oh, this thing has tensor cores inside of it, and it actually can not only do 7.5 petaflops in 64-bit, but it can do 120 teraflops. Each one of the GPUs could do 120 teraflops in half precision. And what that did was get our scientists excited about when you give them an order of magnitude more performance in a particular characteristic, they suddenly start thinking about ways they might be able to exploit it. And that's what it says here at the bottom, is that this modeling simulation community can really benefit it. And I'll show you a couple of examples where people have already started to do that. But in addition, the AI communities and the machine learning can already just take advantage of that super high performance that's built into these NVIDIA GPUs to run very fast. And the way they do it is by doing operations, instead of just doing a floating point operation of 2 items multiplied together or a vector, it actually does 4x4 matrices all at once. Not only that, and Jack Dungara points this out too, it's important to understand that it's not just half precision. So the results can actually come out in half precision or in single precision. The operations of the multiplication are done in half precision, and the addition, though, can also be 32. So it can also be a single precision number. So the actual results coming out can actually be single precision results. And again, that will be important in terms of trying to get real science done at the precision that you need, the accuracy that you need. And we'll talk a little bit about that too. One thing, I kind of shift us a little bit. There were 2 different themes that are going to go through this talk, leading us towards Frontier and an exascale computer. One was, as we move towards exascale, one of the things way back 10 years ago when we first thought about it, and these computers are getting bigger and bigger and bigger, we started thinking that we expect them to become more specialized, and we already start to see people up here talking about, well, we're going to just put a particular accelerator to solve this kind of a problem. We felt like as these machines got bigger and bigger, the number of applications that could really exploit them would get smaller and smaller over time. What Summit has done, and that's been true even for us as we've moved towards Jaguar and Titan, as we move to Summit, suddenly we kind of shifted back because of the features that I just mentioned in these voltas, that this architecture that has sort of these multi-GPU nodes, so very big nodes with a huge amount of memory per node, seems to have stumbled onto a design that has broad applicability. So we've seen a lot of vendors get up here and talk about, well, there's 3 big areas we're doing. We're doing AI now, we're doing data analytics, we're doing simulation. And it turns out that this machine is actually really good at all of those. And here are some examples. I'll spend a little bit more time here showing some real life examples of where Summit has done exactly this. The first example is a case where, so let's just think about a minute the way we try to define what is an exascale computer. So when we started the Exascale Computing Project, we spent days trying to debate how we were going to define it. So one way to define it was just say, okay, if it can do a peak exaflops, it's an exaflop computer. And most people said, oh, that's terrible. Because you could build a stunt machine. Then they would say, well, okay, if it can be an exaflop on the LINPACK benchmark, so the top 500, if it could exceed an exaflop, that would be an exaflop computer. And people would say, well, maybe, but you know, that's really not a really good benchmark, and there's all sorts of reasons why people don't think that's a great thing to do. And again, you might get a machine that's really geared towards just doing LINPACK really fast and not being able to do a lot of other things. And then people would say, well, the harder problem is, can the machine run a real application at a sustained exaflop? And that's typically been the hardest of the 3 goals to try to meet. When we were going petascale, when Titan was able to run the first sort of petascale real application, that was a big deal. Turns out the Summit's already run real applications at over an exaflop, and the 2 of them that have done it so far are both on this slide. The first one has to do with data analytics. The second one is going to be deep learning. The third one is not an exascale, not an exaflop scale, but shows it's excelling in doing a really hard numerical linear algebra problem. But let's talk about the first one. So this data analytics one is an application called COMET, and it's from bioinformatics. It's really all about taking a population. Imagine that you have the genomes for 10,000 people, and what you want to do is you want to find what are the genes that make you susceptible to cancer, maybe a particular kind of cancer. What kind of genes make you susceptible to becoming addicted to opioids? And in fact, that's exactly what this particular run that ran at 2.3 exaflops was really looking for. It was trying to look at the opioid epidemic, so it's doing a really important problem for the country. It's using a really hard situation where you're looking through thousands of genomic databases and you're trying to find out which genes are important and what are the people that are going to be more susceptible to that, so that you would not prescribe opioids in the hospital to people that are very likely to become addicted to them. But it's very generic in terms of how this application runs. It was interesting that the state of the art didn't really run all that well. The scientists at Oak Ridge, this group came in and they were doing these studies, and one of the scientists just had this brilliant idea. Well, let's just throw that code out. There's a really much more efficient way to solve this problem. Completely different algorithm, and that's what I highlighted in red on the slide because of the importance to the people that run this application. They don't care the lick about the fact that it ran at 2.36 exaflops. What was really exciting to them is this problem now solves this particular search, this bioinformatics search, 5 orders of magnitude faster than they've ever been able to do it. 5 orders of magnitude. It's not just like 50 times faster, 1,000. This is 5 orders of magnitude faster. And so now their eyes open up really big when they talk to me about this problem and say, there are a lot of things that we will now take this application and try to solve. What are the genes that are important for poplar trees? What are the genes that make pesticides work well in certain situations? There's lots of stuff that they can do with it. So it's a real application. They've been able to run it on Summit, and it's actually exceed in sustained performance, not over an exaflop, actually over 2 exaflops. The second one is dealing with deep learning. So again, something that this big machine with lots of NVIDIA GPUs can really excel at. And this is not so your traditional, this is more climate simulations. This is what a number of people have talked about already. But this was just a sort of an aside. It's taking the output from a climate simulation and it's trying to identify where are the extreme environments. Where is the Dorian that's going to form the next hurricane or the next tropical storm? If I'm looking at a climate simulation and terabytes of data coming out of this machine, where can I identify by using deep learning? And so that's what they did, and they coded up that particular neural network, trained it, and were able to sustain more than 1 exaop in half precision on Summit. The first one that was actually running at 2.3 was actually getting output in single precision, so it's just an interesting feature. The last one actually is doing something where you're taking advantage of the mixed precision during the calculation, but the actual answer that's coming out is coming to full precision in 64 bits. There, it's just to illustrate, doing something really hard. It's nonlinear, dynamic, low order, unstructured, finite elements. So a lot of really hard things all combined together. And what they did was they were really looking at earthquake simulations, and they were in particular trying to couple very complex situations where you wanted to see the effects on a city where you had buildings with the sort of plasticity of the ground itself. And so the preconditioner for the matrices they were trying to solve was very complicated and not really well defined. And so they used artificial intelligence to generate a preconditioner. So it's sort of a clever way to take advantage of the capabilities of this particular machine for one aspect of the solution and allowed it to run much, much faster to get a much better first guess in that preconditioner so it would converge very rapidly to the full precision answer that they needed. So that particular application ran about 25 times faster than it had been able to do on Titan. And there are a lot of applications that are running on Summit today. I'd say about a half a dozen that are more than 25 times faster. Now, we also heard during the last couple of days there are cases where you get even faster still. So we heard one yesterday that Doug Cothe mentioned and Andrew mentioned in the ECP that was running at like 90x. And in fact, there's another one in there that's running at 143x. And again, these are just interesting cases where this machine seems to be really well suited for a wide breadth of kinds of problems. The reason why 25 is sort of an interesting number is that the machine's only 7 times more powerful in sort of peak than Titan. So the fact that it's running 25 times, the application is 25 times, it's saying it's getting additional boosts because of this architecture that it's built on. This is a gratuitous slide I throw in all the time because it kind of illustrates a different aspect of Summit and its positive features. The previous one says there's a wide breadth of applications that seem to run really well on the machine. This one looks at it from more a system administrator standpoint. It says it's got really high double precision performance. It's number 1 on the top 500. But here's another benchmark that's really data limited, data movement limited, this HPCG. And it ran that one as faster than anyone's ever run that one. So it shows that it not only has high sort of raw performance, it's actually got great data movement inside the machine. Certainly, a lot of times when you build race cars, they are not the most fuel efficient things in the world. But lo and behold, Summit comes along and wins the Green 500, meaning it's also the most efficient machine in the world. So, again, as I want to build an exascale computer, and I'm looking around, well, how should I build it? It's like, well, I should look and see what Summit is built like, and see if there is kind of the next generation of what that might look like. So what makes the Summit architecture so much better than Titan? So one is, it has many fewer nodes. As you can see in the little table, we're not going to go through the table, but it'll illustrate each of these points. Many fewer nodes. Titan had 18,000 nodes in it. And all of a sudden we tell our users, now you only have to program to 4,000 nodes. And players think, glory be. Thank goodness for that, because we were worried that you're going to come to us with a machine with 50,000 nodes in them. One is, then each of those nodes is very powerful, so they can think of just kind of using a few of them. So Titan only had about 1.5 teraflops. This Summit's got more than 40 teraflops of performance in each node, and there's coherent memory across that node, so it makes it much easier for me to program. It makes it easier for me to say, gosh, I can't use all 6 GPUs, but I could use 2 GPUs, but all the memory on the node, because it's all coherent. Everybody can see all the other memory. And that's another point about it, having a lot of memory on the node and much higher bandwidth. It's got the faster interconnect, and the bandwidth between the CPU and GPU is much better than Titan. That was really the bottleneck in the Titan design, and Summit sort of eliminated, and we wanted to make sure as we move forward to Frontier that it would also be eliminated there. It has a much larger and faster file system than we had in Titan. In Titan, we had something more common to what you've heard about today. It was a 32 petabyte file system, about a 1 terabyte per second bandwidth to it. And then Summit, as I mentioned before, it's 250 petabytes and 2.5 terabytes per second. One of the interesting things about the performance of how much power it used, as you see on this chart, you can see that Titan had a maximum sort of peak possible draw. It's never drawn this much, but 9 megawatts. If it was all lit up, every piece of electronics in it was lit up, it could pull 9 megawatts. Similarly, Titan could pull 13 megawatts if you lit everything up. But even when we ran HPL on Titan, it only drew 8.8 megawatts. So it didn't even get as high as the peak of Titan, even though it's a much more powerful machine. So it's just showing how much more power efficient these particular machines are. So, as we kind of wrap up then on this last slide, I want to show how we've taken that and moved us towards the Frontier design. So it continues this, many of these features that we saw worked really well in Summit. So the Frontier node, as I gave you the hint before, it takes the next step. So it's got 4 GPUs per CPU. It has one AMD EPYC processor. Several people have mentioned the Frontier's design. Stephen Scott did. The folks at AMD mentioned it. It's got 4 HPC and AI optimized AMD GPUs inside of it. It's fully connected across all the CPUs and GPUs like we had in Summit, and it's coherent memory across that entire node, again, just like we did with Summit. And it has this on-node NVM storage. It turns out that turns out to be a really important feature, not only for some AI applications, but more importantly for the way that you deal with resilience on these really big machines. Being able to checkpoint a job in a few seconds rather than in a few minutes allows you to get away with failure rates that are supposedly higher on these machines. I think that the rest of the bullets here are things that you've seen on other slides, except for maybe this one here, that the maximum power consumption then on Frontier is actually below 30 megawatts. So that's another interesting feature that, again, is showing that the power of these machines is not growing exponentially like we worried they were. I think a lot of that has to do with the ECP project. They invested a lot of money in Path Forward to try to allow the vendors to try to figure out ways to build more power efficient chips and systems, and they've sort of come up with a great solution in that regard. And with that, I thank you, and any questions? Yes, sir.
When you were talking about your 5-order of magnitude speed up, are you talking about a 5-order of magnitude reduction in the compute time to do it, or the clock time on the wall?
The compute time decreased 5 orders of magnitude. You would still inject it into a queue, and you'd get back the answer when it ran, but it would run in a very much faster. So they didn't really think of it in terms of, okay, now it runs much faster. They thought about, now we can solve much bigger problems or much harder to describe problems. We're looking for something that's much harder to define. Which gene makes this pesticide work? What gene makes this tree grow faster?
So that kind of begs the second question. So some of that was due to the physical architecture of the machine, the hardware, and some of it was due to the fact that you changed the algorithm.
Most of it had to do with changing the algorithm. Exactly, there was. So what they did is Wayne Jobert is actually the person who is the genius that happened to see a new way to design the algorithm for this machine, or for this particular problem. And the core of that algorithm turned out to be a matrix multiply that they could then exploit the tensor cores on, almost exclusively. As you might imagine, to get to 2.3 exaops, the machine peak is only 3.3 exaops, sort of flat out every cycle you're doing one of those 4x4 multiplications. And so it actually, he came up with an algorithm which actually solved the right problem, but also used most of its time doing the very thing that this machine is really well suited for. So that was a really great advantage for him. Yes?
Each node had 1.6 terabytes of, terabytes, I believe it was, of
non-volatile memory. Yes, sir.
Was that NVDIMM? Was that, what was that?
It was well, it's actually shown on here, but it was a single SSD sitting off of here. This NVM right here. So it's plugged into only
so
one
that was
of
a
the
solid-state drive.
It's a solid-state drive, yeah.
Okay.
It was, I didn't put an actual physical picture of the board, but you can actually see an SSD, a very tiny one, set right in beside the processor, because they could just slip it right in there.